today onwards we'll be doing another important chapter in terms of level of difficulty, that is transportation problem. It's a little more difficult than assignment problem. There are a lot of variations. This problem has to be solved in 2 phases and so on. I'll take you through the entire process of phase 1 right now. Phase 1 and phase 2. I'll explain what is phase 1 and phase 2. Before that, I'll read this question from the book that is there with you. This is question number 1 from the transportation problem. Phase 1 is what I have written here. We'll be solving this problem for phase 1 and phase 2 as well little later, but before that we'll be tackling phase 1. So I'll read out the problem for your benefit. Question number 1. Solve the following transportation problem for minimizing the cost of transportation if the numbers in each cell represent unit cost of transportation. In other words, whatever is given inside the cell are unit cost of transportation. And the other numbers, I'll explain the meaning of them as we go ahead. Now, this is therefore the given problem which I need to solve. This is a transportation problem, question number 1 from your book. Now, what this problem stands for, I'll explain. This is, if you see, the names of the rows are O1, O2, O3 and O4. That means there are 4 rows with the names O1, O2, origin 1, origin 2, origin 3, origin 4. The names of the columns here are D1, D2, D3. D stands for destination. So, destination 1, destination 2, destination 3. These are the names of destinations. Now, these are actually in real life, these are places. For example, it could be Mumbai, Delhi, Kolkata, Madras, etc. Okay. So, these are places. Now, the objective is to minimize the cost of transportation, and therefore, usually the transportation cost is proportional to the distance. For example, transportation cost from Mumbai to Pune is going to be much less compared to Mumbai to Bangalore, correct? So, obviously, the transportation cost usually proportional to the distances involved, and therefore, here we have the cost of transportation. What it suggests is, if I want to transport 1 unit of commodity, what is a commodity? It could be cement, it could be steel or any other commodity. It could be 1 bag of grain which needs to be transported from one place to another place. For example, from O1 to D1, if I want to take 1 unit of goods from O1 to D1, the cost involved is 7. 7 could be 7 rupees or 7,000 rupees or $7. It's some monetary unit or money value. Okay. O1 to D2, the cost would be 10 or 10,000, whatever the numbers stand for. O1 to D3, the cost would be 5. Okay. So, this is what the entire matrix tells me. As you can see here, the highest cost is from O2 to D1, which is 12. And the lowest cost in the whole matrix is 3. That means O3 to D2, the cost is lowest at 3. So, taking 1 unit from O3 to D2, it is going to cost me only 3 rupees or 3 monetary units, and from O2 to D1, it is going to cost me as high as 12 units. So, the numbers inside the cell are the cost of transportation. Lowest here is 3, highest here is 12. Fine. Now, what are the numbers at the end of the rows and columns? You will find row number 1 has 90, then 50, 80, 60, and similarly there are numbers at the end of each column. What do these stand for? Okay, I'll explain. O1, for example, origin 1, origin 2, origin 3, origin 4 are 4 places from where the goods are being transported out. And where are they going? They are going to destination D1, D2 or D3. We have a choice. We have a choice of choosing where from O1, whether from O1 I will send goods to D1 or D2 or both or only D3. The choice is with me. My objective is to minimize cost of transportation. Okay. Now, what are the numbers at the end of the row? 90 I have written at the end of the row means at O1 origin, 90 units of the commodity are available. That means O1 has a capacity of 90 units. Similarly, O2, O3 and O4 have capacities of 50, 80 and 60 units respectively. So, what is the total availability at O1, O2, O3, O4? It is 90 plus 50 plus 80 plus 60. That is 280. 280 units are available for transportation. Okay. Now, what are the numbers at the end of each column? 120, 100 and 110. They are the numbers at the end of columns. What this means is the demand at destination D1 is 120 units. Totally D1, the destination D1 requires 120 units of commodity. Destination D2 requires 100, destination D3 requires 110. Okay. So, these are the demands. Now, what is the total of demand? It will be 120 plus 100 plus 110, that is 330. That means the demand is 330. The availability here, which is total of these numbers, is 280. Okay. So this is the available situation. We need to solve this problem for transportation in such a way that the total cost of transportation is minimum. Okay, fine. So how to go about it? See, unlike assignment problem, transportation problem has two phases of solving, phase 1 and phase 2. Right now we are doing only phase 1. Phase 1 obtains what? Phase 1 obtains a solution, one solution to the problem. Now, whether that solution is optimal or best is not known until we go to phase 2. And there are several methods of obtaining the solution in phase 1. There are 3 methods which are mentioned in your study notes, or for that matter, even for our MBA programs or BMS. Usually we are doing these 3 methods, but there are more methods than 3 which are available. We will be restricting ourselves to only 3 methods, but everywhere usually only these 3 methods are covered. So we will be getting phase 1 solution by all the 3 methods. Okay, fine. But like transportation problem, like assignment problem, there are pre-checks over here also. First pre-check. So I'll write down what are the pre-checks. You will be happy to note that the pre-checks are same. The pre-checks are same as in respect of assignment problem. First pre-check, is it a minimization problem? Okay, so is it minimization? If not, convert. Second pre-check, is it balanced? If not, balance it. So the pre-checks are same as in the case of assignment problem, but the way the pre-checks are done is slightly different. I'll explain now. First pre-check, is it a minimization problem? The question clearly says that these are transportation costs, and transportation costs are obviously required to be minimized. For example, in another matrix, these could be profit numbers. In case these are profit numbers, then it is not a minimization problem. The objective of the problem will be to maximize profit. And therefore, this problem as given is for minimization itself. So I say the first pre-check is successful here. Okay. Second pre-check. Second pre-check is it a balance problem? Now here in case of assignment problem, if you recollect, we just said if the number of rows is equal to number of columns, the problem is balanced. That is not the case here. The case here is like this. What is the total availability and what is the total demand? Now availability is written at the end of various rows. Now what is the total availability here? O1, O2, O3, O4 have availability of 90 plus 50 plus 80 plus 60, which is 280 units are available. In other words, in this case, the amount of commodity, the number of units of the commodity available for transportation from O1, O2, O3, O4 is 280 units. Okay. So availability, I'll say availability is 280. Now what is the demand? Now demand is indicated at the end of the column. Destination 1 has a demand of 120, destination 2 has a demand of 100, destination 3 has a demand of 110. This totals to 330, different than the availability. Availability is 280, demand is 330. So demand is equal to 120 plus 100 plus 110 equal to 330. These numbers are not same. Availability is 280, demand is 330. Obviously, when the availability is less than demand, I will not be able to satisfy the entire demand because I have only 280 units of commodity available, whereas in demand, the number of units are 330. That means there is a shortfall to the extent of 330 minus 280, that is 50 units are short with me. I will not be able to satisfy some demand to the extent of 50 units. Out of a demand of total 330 units, I will be able to satisfy demand only to the extent of 280 units, and some demand to the extent of 50 units will remain unsatisfied. So this problem is therefore not balanced. So how do you find out whether a problem is balanced or not? Just total the availability and the demand. See if they are same. Okay, if the demand and supply are same, we say that the problem is balanced. For example, if both the totals here were 280, then I would have said that the problem is balanced. The number of rows and number of columns has no relevance. Okay, here there are 4 rows and 3 columns. In the given problem, there are 4 rows and 3 columns. It does not have any implication whether it is balanced or not, depending on the number of rows and number of columns. What is important is what is the total availability and what is the total demand. The total availability here is 280, which is nothing but 90 plus 50 plus 80 plus 60. 280 units are available. 330 units are demanded, which is nothing but 120 plus 100 plus 110. 330 units are demanded, 280 units are available. What we immediately note is we will not be able to satisfy the entire demand, we will be able to satisfy demand only to the extent of 280. Sometimes the unbalanced part of the problem may be because the availability is more and demand is less. For example, if I turn this problem through 90 degrees, the availability will become 330 and the demand will be 280. In which case, the entire demand will get satisfied, but I will have 50 units excess available with me. When the availability is 330 and demand is 280, what will happen is the entire demand of 280 will be satisfied and I will be still left with 50 units which are excess supply with me. So either there is excess supply or there is excess demand. In either of the cases, we say that the problem is not balanced. We cannot apply any algorithm when the problem is not balanced. So what do we do? Now find out here. Is the availability less or the demand is less? Availability totals are at the end of the rows. Demand totals are at the end of the columns. Here the availability is 280 and demand is 330. That means availability is less by 50 units to 330 minus 280. 50 units are short supply and therefore we need to create an additional supply. I must increase the lower of the two values to match the higher value. 330 is the higher value, 280 is the lower value, therefore I need to increase 280 to 330. That means I need to create another origin called as O5, which will have 50 units available with it, so that the total availability will become 280 plus 50, 330, and the demand is already 330, then the problem will become balanced. In other words, I need to add. When the demand is more and supply is less, I need to add a row. When the supply is more and demand is less, I need to add a column. Okay. Now let me therefore write down the new problem. Since the problem is not balanced, I am balancing it now. So instead of a 4 by 3 problem, now there are 4 rows and 3 columns. It is going to become a 5 by 3 problem. In the sense, there will be 5 rows now. Instead of 4 rows, I am making it a 5 rows problem. Now see here. Now what are the names of the origins? O1, O2, O3, O4 as before, and I am adding origin O5 because I need additional supply of 50 units, so that will be available in origin O5. Now these numbers were known already: 90, 50, 80, 60. And what is this? The difference between the original demand and supply was 50. So I am writing here 50. And this was 120, 100, 110. Now if you total up the availability and if you total up the demand, it is same. So now it has become a balanced problem. My second pre-check had failed. It was not a balanced problem. Now I have balanced it. In this process, however, I have created an additional row. The original problem, which had a size 4 by 3, has now become a 5 by 3 problem because it has 5 rows and 3 columns. So now I am writing the cost, just copying the numbers from here: 7, 10, 5, 12, 9, 4, 7, 3, 11, 9, 5, 7. Like in the case of assignment problem, we have here a virtual row. Virtual row O5, the origin which does not exist. Therefore, when you add a row, or for that matter add a column, it's either a virtual row or a virtual column as the case may be. And therefore, the cost of transportation in that added row or added column are to be taken invariably as 0. In other words, I am taking these numbers as 0. When a row is added for the purpose of balancing, we are taking the numbers in that row as 0. When a column is being added, for that matter, when in the other situation, that column also will have all zeros. Now both my pre-checks are successful. Is it a minimization problem? It was already a minimization problem. Is it a balance problem? Now it is a balance problem, because if I write the totals in this way, this is total of row availability is 330, total of column demand is also 330, and therefore this becomes a balance problem. Fine. Now important thing, we are coming to the algorithm. See, first two pre-checks are important. Then we go to phase 1. Now what is phase 1? Why are there phases, phase 1 and phase 2? See, here the transportation algorithm is solved in two phases, in the sense phase 1 just obtains a solution to the problem. A solution meaning that solution may be good enough, it may not be good enough, but it's a solution nevertheless. And what is a solution to a transportation problem? The one which satisfies the demand and supply condition. That means the total availability in row number 1 is exactly 90, total demand in column number 1 is exactly 120. If that is the case, this is a feasible solution. So therefore the phase 1, purpose of phase 1, I'll write here phase 1. Objective. What is the objective? Get a solution. We call it get basic feasible solution or initial feasible solution. This is sometimes known as BFS for basic feasible solution or IFS initial feasible solution. Okay. Now these two words are used, BFS or IFS. In the CA study notes particularly, the word which has been used is BFS or basic feasible solution. In some of the textbooks you will find a word IFS. IFS and BFS mean the same thing. Basic feasible solution or initial feasible solution, which is what? End result of phase 1. And end result of phase 1, the purpose is to obtain IFS or BFS or a solution to the problem. Done. We'll be doing this. Now what is the method followed for obtaining an IFS or BFS? Actually there are three different methods which we'll be covering. Okay. Now I'll write down the names of the methods first. Now this is phase 1 methods. First one I'll call it NWCR. What is NWCR? It's a short form for Northwest Corner Rule. Northwest Corner Rule. NWCR for short. Northwest Corner Rule. Second method, again the purpose is same, remember, phase 1. Phase 1 purpose is what? Get BFS, also known as IFS. So all these three methods can be used to obtain BFS or IFS. Which of these three methods should be normally used? I'll explain when we go there. Okay. Now second method known as LCM, or this is, I'll call this as Northwest Corner Rule, or sometimes also known as Northwest Corner Method. This LCM stands for Least Cost Method. Short form LCM, Least Cost Method. In some cases it is also known as Matrix Minimum Method. So LCM or Matrix Minimum Method, MMM. MMM. Matrix Minimum Method or Least Cost Method. Both mean the same thing. Somewhere the words used are LCM, in some places you will find the word used is MMM. The purpose is same. This is least cost method, this is matrix minimum method. The methods are same actually. These are two names for the same method. And the third and the most important method, as we will be seeing, is called as VAM. VAM standing for Vogel's Approximation Method. Long form for VAM is Vogel's Approximation Method, VAM. These three methods are used for obtaining the solution in phase 1. So the procedure is like this. While solving a transportation problem, any transportation problem for that matter, we must obtain IFS or BFS. Which method do we use? We can use any one of the 3 methods. And what does this do? It gives only a solution, which is nothing but a starting point for phase 2. So phase 2 starts where phase 1 ends. The purpose of phase 1 is to get in place a BFS or an IFS. Which method do we use? We have 3 methods to be used: northwest corner rule or northwest corner method, LCM or MMM standing for least cost method or matrix minimum method, and last one VAM or Vogel's approximation method. Vogel is the person who discovered this method, that's why his name has been given as Vogel's approximation method. Fine. So given this, today our objective is to try and obtain IFS using all these 3 methods. Okay. So I'll be showing you the solution by using all these 3 methods. So we'll go to northwest corner rule first. So what am I doing? I am in phase 1. Right now I am going to be in phase 1 for a long time. In phase 1, there are 3 methods, of which I am doing method number 1 called as NWCR or northwest corner rule. Okay, fine. So this is my matrix now. Remember, this matrix is not relevant anymore. Okay, this is my new matrix. So this matrix has served the purpose. What did I do by way of modification to this matrix? I have added a row for the purpose of balancing, because the demand and supply was not same. The demand was more, supply was less. Therefore, I have created additional supply of 50. Thereafter, the problem became balanced. Both were numbers of demand and supply are 330. So, I am removing this original problem. We'll come back to this original problem at the end while giving out the solution in a structured manner. Okay. Now, for the time being, I am removing these totals. These are not required now, because we have just checked that the totals are same. Okay. Now, what I am doing is, remember always O1, O2, O3, O4, O5, etc. will be names of origins. D1, D2, D3, D4, etc. will be names of destinations. In the given problem, we have O1 to O5, 5 origins, 4 real, 1 virtual. D1, D2, D3 are my 3 destinations. So this is a 5 by 3 problem. There are 15 cells in this matrix, 5 rows into 3 columns, 15 cells. Fine. Now I am trying to obtain the solution by northwest corner rule. Now what is northwest? Let me explain. If you see map of any country, you will find this symbol in that map. What does this symbol mean? This symbol means that this is north. When this is north, obviously this is south. And this is east and this is west. This east, west and south are not written, but once you write the north, the remaining 3 things are fixed. Where is east, where is west and where is south is known. You only need to know where is north. So this symbol you will find in each and every map. So what is northwest? Northwest is up, north, and west is to the left. Correct. So in this matrix, therefore, what is north? North is up and west is to the left. So which is the northwest corner? Northwest corner is here. Okay. I am calling it D1, D2, D3. So cell O1, D1 is the northwest corner of this matrix. Okay. In fact, if you name the rows as O1, O2, O3 and destinations as D1, D2, D3, do you find that O1, D1 cell will always be the northwest corner of any matrix? Whatever be the number of rows and number of columns, cell O1, D1 will always lie at the top and it will always lie to the left, and therefore cell O1, D1, which is this cell, is the northwest corner of this matrix. Now look at this cell. This cell O1, D1 tells me that the total availability at O1 is 90 units. And total demand at destination D1 is 120 units. What is available in O1 is 90 units. What is demanded at D1 is 120 units. So my question is, how many maximum units can you transport from O1 to D1? Now see, O1 has availability of 90. D1 has demand of 120. So what is the maximum number of units you can possibly transfer from O1 to D1? It will be 90. Correct? Why? but it will be lower between the supply and demand. What is the supply and demand for this cell, for example? This cell, that means O4D3. This cell can be called as O4D3. In O4D3, what is available is 60, what is demanded is 110. So how many maximum units can I send from O4 to D3? Lower of these two, 60. Because obviously I cannot transport more units than are available, or I cannot transport more than what is the demand for the place. Therefore, for any cell, I can say, for example, this cell, if I take up O3D2, the availability is 80, demand is 100. So what is the maximum number of units I can transport from O3 to D2? It will be lower between 80 and 100, that is 80. Okay, fine. So let me transport therefore maximum number of units in the northwest corner, which is O1D1. O1D1, I find that the availability is 90, demand is 120. So the maximum number of units which I can transport from O1 to D1 is 90. Fine. So O1 to D1, 90 units have been transported. Now the moment I make an allocation in a cell, I put it in a circle. The circle is an allocation. The number outside the circle is unit cost of transportation. This suggests that if I transport 90 units from O1 to D1, the cost being 7, the total cost involved for 90 units will be 90 into 7, that is 630. Okay, the cost of this particular cell right now will be 90 into 7, that is 630. Now with this allocation, what has happened is the entire availability at origin O1, which was 90 units, has got fully exhausted. See, I have total 90 units available at O1, of which I have already transported 90 units. That means nothing else is available at origin O1. That means the origin O1 availability is finished. So I need to therefore delete this row. No more availability in origin O1. But what has happened to destination D1 demand? Destination D1 had a demand of 120, of which 90 units have been supplied already from O1. So there is still a balance demand of 120 minus 90, or actually 30. 30 units are still needed at destination D1. Okay, because out of a demand of 120, 90 has already been satisfied from O1 itself. From O1 I have already transported 90 units to D1. As a result, the total demand for D1, which was 120, stands satisfied to the extent of 90. So balance demand in destination D1 is still now 30 units. Fine. So first allocation successfully made. What is the method that we are following? NWCR. This is method number 1. I am doing the allocation using NWCR, or northwest corner rule. Now see, one allocation has been made. Now next allocation. What is the situation here? One row has got deleted from the matrix. That means the original matrix, which was 5 by 3, has become now 4 by 3. There are only 4 rows left and 3 columns are left. Okay. Now pick up the northwest corner of this matrix. Which is the northwest corner of this matrix? What is northwest? Uppermost, leftmost. So uppermost and leftmost will be this cell. It can be called as O2D1. It can be called as O2D1. Therefore, O2D1 is the cell which is now the northwest corner of the matrix. Okay. Now O2D1, what is the situation here? O2D1, when I look at this cell, the availability here is 50, but the balance demand is only 30. And how much therefore I can allocate maximum in O2D1? Lower of demand and supply. Supply is 50, demand is 30. That means I cannot allocate more than 30. I cannot be allocating more than the demand of the place, or I cannot be allocating more than what I have. I have 50, but the demand is only 30. Therefore, I am allocating only 30 units from O2 to D1. Allocation is shown in a circle here. With this, what happened? This entire demand of 30 had got satisfied. Therefore, this column needs to be deleted now. Okay, so I'll delete the column. And what happened to availability at place O2? O2 has availability of 50, of which 30 has been already supplied. So what is the balance availability? 50 minus 30, that is 20. Okay. Fine. So I have made two allocations, two numbers shown in circle. First two allocations using northwest corner rule are already made. Continue the same procedure. Okay, continue the same procedure. That means of the remaining matrix, what is the remaining size of the matrix? There are 4 rows and 2 columns only now. What is the northwest corner? Northwest corner will be always uppermost, leftmost. So what is the uppermost, leftmost corner? This is the uppermost, leftmost corner. Now what is the situation here? The availability is 20 and the demand is 100. So what is the maximum quantity which I can allocate from O2 to D2? Lower between 20 and 100 is 20. So I'll allocate 20 units over here. Okay. Once I do that, can you see that the availability at origin O1 is finished? I had 20 units. I have already allocated them here. So see, remember totally there were 50 units at O2, of which I have allocated 30 here and 20 here, making a total of 50. So availability at O2 is finished. But what happens to the demand of destination D2? Destination D2 has a total demand of 100, of which 20 is already supplied. Therefore, balance demand at destination D2 is 100 minus supplied 20, so 80. Okay, great. Now look at the remaining matrix. Now what is the size of the matrix? 3 by 2, 3 rows by 2 columns. This is the northwest corner, uppermost, leftmost. What is the situation on availability? It is 80 units available, 80 units demanded. So obviously I can make allocation of maximum 80 units. So I make allocation of 80 units. But with that what happens is not only the row gets cancelled, even the column gets cancelled. So I am saying because the row availability is finished and column demand is satisfied at the same time, I am deleting row and column at the same time. Now what is the situation? 2 rows left and 1 column left. In any of the 3 methods, whether you are following northwest corner rule or whether you are following least cost method or whether you are following Vogel's approximation method, this situation will always come. The situation, only 1 row is left or only 1 column is left. Have we reached that situation? Yes, because only 1 column is left now. Only column which is left is over here. Out of 3 columns, I have already cancelled 2 columns. So 1 column is left, but 2 rows are left. When you reach this situation of only 1 column or only 1 row left, you do not have any choice about making allocations. For example, here the availability is 60, demand is 110. Here the availability is 50, demand is 110. As you can easily see, total availability is 60 plus 50, 110. Total demand is 110. Since only 1 column is left, I have no choice. I need to make an allocation of 60 here and 50 here, and that will complete my initial feasible solution. Okay. So this because the demand is satisfied, supply is finished. This because the demand is satisfied, 60 plus 50, 110. So I have obtained the solution using northwest corner rule. This is a solution. I do not know whether the solution is good enough. That will happen. This will be checked in phase 2. But right now we are doing only phase 1. There are 3 methods for phase 1 as I explained. Northwest corner rule was the first method. We obtained the solution using northwest corner rule. What is the cost involved in this process? Let's just find out the cost involved. Now if you see, what is the cost? Let me calculate the cost. 90 units have been allocated at a cost of 7. So 90 into 7, 630. Second, 30 units have been allocated at a cost of 12. So 12 into 3, 360. 20 units have been allocated at a cost of 9. So 20 into 9, 180. Next, 80 units at a cost of 3. So 80 into 3, 240. Here, 60 units at a cost of 7. So 60 into 7, 420. And 50 into 0, last row was created by us, so it is 0. This is the total cost of transportation for phase 1 solution using which method? Northwest corner rule. So what is the total? 1830. This is the total cost of transportation for phase 1. Just check the total. $1830. So I'll say northwest corner rule, I got a cost of 1830. Okay, fine. So this solution, let's count the number of places where there is an allocation. Now see, total cells in this matrix are 5 by 3, 5 rows by 3 columns. So 15 cells are there in this matrix. At how many places have we made allocation? 1, 2, 3, 4, 5 and 6. 6 places we have made allocation. Out of 15 cells, there is allocation in 6 places. That means there is no allocation in the remaining 9 places. Okay. So I'll write here, number of allocations is 4 and 2, 6. 6 allocations have been made. The total cost of transportation is 1830, and we have completed phase 1 solution using northwest corner rule. Now, a very interesting thing has happened in this process. Can you see that we never considered the cost in the cell? For example, I said that the costliest cell in the matrix is 12, and I have made an allocation there. Because northwest corner rule, what does it do? It only picks up the northwest corner, goes on making allocation. Pick up the remaining, find out the remaining matrix, pick up the northwest corner, go on making allocation. As a result, what happened is, I made allocation in the costliest cell also, and in the process, I have also made allocation in the least cost cell also. So this method, which does not even consider the cost of transportation in a cell, must be the most inefficient method for obtaining solution, and it is. As we'll see now, when we make comparison of this solution with the next solution, you will find that we are making some improvement. Because as the name suggests, the name of the second method is least cost method, or LCM, or matrix minimum method, called as MMM, matrix minimum method. So now obtain the solution using, I have already completed northwest corner rule. Now I am going to method number 2. It is known as least cost method. So let me write down this matrix again. I will obtain the solution using least cost method. Remember, all the solutions that we are obtaining right now are only phase 1 solutions. They may be good, they may not be good. Okay, fine. So let me write down the matrix. I have noted the cost. Cost is 1830. So I am drawing this matrix once again, and I am applying method number 2, called as least cost method or matrix minimum method. Now I am rewriting the matrix, 5 by 3 matrix. So I am drawing a 5 by 3 matrix. 5 rows, 3 columns. Let me write down the demand supply situation. 90, 50, 80, 60, 50, 120, 100, 110. This was the balancing row, therefore I know the cost was in this row was 0. Now what are the costs? 7, 10, 5, then 12, 9, 4, 7, 3, 11, 9, 5, 7. I am not writing the names O1, O2, O3, etc., or D1, D2, D3, etc. They are obvious. Always remember, the names of rows are O1, O2 onwards, and names of destinations are D1, D2 onwards. Now, I want to find out the IFS using the second method, called as least cost method. So I will call it method number 2. LCM. I will verify what is the cost at the end of this solution, and we will compare the solutions of northwest corner and LCM. Okay. The least cost method, as the name suggests, has something to do with the least cost. Least cost means, now see, we have started looking at the cost. Northwest corner rule ignored the cost. It went on making allocation by virtue of the position of the cell in the matrix, whereas least cost method will verify the lowest cost in the matrix. Now look at all the cost of various cells. The costs are ranging from 0, which is lowest, to 12. So the least cost in the entire matrix is 0. Okay. So choose the cell with the least cost. And I find that there are 3 cells with the least cost. 0 here, 0 here, and 0 here. Okay. 3 places where I can make an allocation. Okay, confusion. So where should I make the first allocation? I'll say make it in any place. But usually we follow this rule. Now suppose I want to make allocation here. What can the allocation be? The availability is 50, demand is 120. That means I can make allocation of maximum 50 units, lower between demand and supply. Supply is 50, demand is 120. I can make maximum allocation of 50 units. If I take this cell also, availability is 50, demand is 100. So I can make allocation of only 50 units, lower between 50 and 100. Same here, lower between 50 and 110, I can make allocation of only 50 units. So again confusion. I can make allocation either here or here or here, and all the allocations are going to be 50. So how do we do it? Now see, there is one shortcut which can be useful sometimes. Find out what is the difference between demand and supply. Okay, if I make allocation here, 50 and 120, the difference between demand and supply is 70. Next, 50 and 100, the difference between demand and supply is 50. Here the difference between demand and supply is 70, here it is 50, and here it is 60. Choose the lowest of them. Allocations can be 50 here, 50 here, or 50 here. But which of these three 50s I will choose? I will choose that particular 50 where the difference between demand and supply is lowest. Here the difference between demand and supply is 70, 120 minus 50. Here it is 100 minus 50, so it is again 50. And here it is 110 minus 50, or 60. So here the difference is 70, here it is 50, here it is 60. Which is the lowest of the differences? 50. Therefore, I will make allocation over here. Okay. So, but actually, whether you make it here or here or here, the allocations would be correct. The allocations would all be correct. But sometimes a more efficient allocation is obtained if I consider the difference between demand and supply being lowest. So, I will therefore make allocation over here, and I will call it 50, which is lower between the demand and supply. Okay. Now, allocation has been done to the extent of 50. With this allocation, since I am making highest of the allocations, what is the highest allocation which I can make? Lower between the demand and supply for that particular cell. I decided to make allocation here. That supply was 50, demand was 100. So I can make maximum allocation of lower between demand and supply, which is 50. So I made allocation of 50. After every allocation, whether you are following least cost method or NWCR or for that matter Vogel's method, either a row or a column has to get cancelled because you are making maximum possible allocation. Now see, with this allocation of 50, can you see that the supply has been fully exhausted? Therefore, I need to delete this row. And what happens to the column demand? Column demand was earlier 100. Now out of 100, I have satisfied demand to the extent of 50. So what is left is balance is 50. Fine. Now do you remember that we have started with a balance problem? Always we have to start with the balance problem. Therefore, after making any allocation, the balance remaining problem will always be a balance problem, and the demand and supply would be same. In other words, 90 plus 50 plus 80 plus 60, 280 will total up to 120 plus 50 plus 110. This is also 280. The remaining problem will always be balanced because we are deleting equal quantity from demand and supply. The remaining problem will always remain balanced. Now look at the remaining matrix. Last row is gone. All the lowest cost cells of 0 are gone. In the remaining matrix, pick up the lowest cost. What is the remaining matrix lowest cost? It appears to be 3. So I'll choose this cell for making an allocation. This cell for making an allocation, that means O3D2 cell, how much allocation is possible? I have availability of 80 units and the demand is 50 units. Therefore, what is the maximum quantity which I can allocate from O3 to D2? Why am I choosing this cell? Because out of the whole matrix, this is the lowest cost. Therefore, I am choosing this cell. What is the name of the method? Least cost method. So, at every stage, you find out the least cost in the matrix. This is the least cost in the matrix. 80 units are available, 50 units are demanded. Therefore, my allocation can be maximum 50 units. So, I make this allocation. And with every allocation, either a row or a column has to get deleted. Can you see here the column will get deleted because the demand was 50. fully satisfied, and therefore this column stands deleted. Okay. What about row availability? This row had 80 units available, of which I have already supplied 50. So what remains is 80 minus 50, that is 30 units. Done. Next, now look at only the remaining matrix. The remaining cells are these 4 and these 4. This column is gone. Okay. Now out of the remaining cells, which is the lowest cost? Now it is 7, 12, 7, 9, 5, 4, 11, 7. So the lowest cost is here, which is 4. For this cell, what is the name of the cell? O2D3. O2D3. In O2D3 cell, the availability is 50 and the demand is 110. So what is the maximum quantity which I can allocate? Lower between 50 and 110, that means 50. So I allocate here 50 units. With this, whether a row will go out or a column will go out, can you see? The row will go out, because the availability was 50. It is entirely exhausted by making allocation here. That means this row will stand deleted. And what happens to the demand of 110? 110 is satisfied to the extent of 50. Therefore, the balance demand in destination D3 is now 110 minus 50, that is 60. Okay. Now look at the remaining matrix. What are the costs? 7, 7, 9, 5, 11, 7. Look at the only cells which are not yet deleted. So out of this, lowest cost is here, 5. 7, 5, 7, 11, 9, 7. Out of all these, lowest cost is 5. Why are we choosing lowest cost? Because the method is least cost method. So at every stage, we are choosing the least cost. So what is the least cost? 5. I need to make allocation over here. The availability is 90, demand is 60. So how many units can I allocate maximum? 60, lower between demand and supply. So 60 units are now allocated in cell called as O1D3. With that, can you see that this column will have to be deleted, and therefore this column stands deleted. And what happens to 90? 90 becomes 90 minus 60 or 30. Good. Now see, out of 3 columns, 2 columns have been deleted. So have we reached a situation where only 1 column is left? Many times you will reach a situation where only 1 column is left or only 1 row is left. In each and every method, whichever problem you are solving, you will always reach this situation where only 1 row is left or only 1 column is left. Now how many cells are remaining? In the matrix, 7, 7 and 9, that means O1, D1, O3, D1 and O4, D1 are the only cells which are left. Only 1 column is left. When only 1 column is left or only 1 row is left, you do not have a choice about making allocations. So what does it mean? Balance demand is 120, this column deleted, this column deleted. Balance demand is 120. What is the balance availability? 30 here, 30 here and 60 here. 30 plus 30 plus 60, 120. Demand is 120. That means I must make the entire balance allocations of 30 here and 60 here. That means 30 over here, okay, 30 over here, okay, and 60 over here. Fine. All the demand and supply has been satisfied, and all the rows and columns need to be now deleted. Great. So this is the solution obtained by applying the method called as LCM or least cost method. Let's see if we have made an improvement on the cost front, because see, we started applying our mind on the cost. Northwest corner rule, if you remember, it ignored the cost. We never considered even the cost of the cell. So what did we do? We went on making allocation in the northwest corner, irrespective of the cost. Do you remember we had made allocation even in this cell? Do you see here? Highest cost cell. We had made allocation there also. But here we consciously chose cells which have least cost, and therefore one by one we have taken full advantage of the least cost, and therefore hopefully the cost of transportation now is going to be most probably less than the previous cost. Let us do a calculation. Now see, 30 units at 7, 30 into 7, 210, 60 into 5, 300. Cost of transportation is 300. For this cell, this cell. What about this cell? 50 into 4, 200. So I have considered 3 cells. Now fourth cell, 30 into 7, again 210. Next, 50 into 3, 150. Next, 60 into 9, 540. And then 50 into 0 would be 0. So what is the cost? $1610. Can you see that the moment we started applying our mind on the cost has started reducing. So the method number 2 appears to be more efficient than the method number 1. So this way we have obtained the allocations for northwest corner rule and least cost method. The difference is of course in the cost. One is the difference in the cost. We got a cost of 1830 or 1830 using the northwest corner rule, and the cost that we managed to get using least cost method was lower at 1610. Now the important another difference that will come, and it will get importance in phase 2, is how many allocations are there here. 1, 2, 3, 4, 5, 6. So we said in NWCR we got 6 allocations. And in least cost method, how many allocations did we get? 1, 2, 3, 4, 5, 6, 7. So we got 7 allocations. The number 7 is significant and it is important for this particular problem, which I will explain after we get the allocations by Vogel's approximation method. So now we are obtaining IFS or BFS, basic feasible solution or initial feasible solution. As I said, there are 3 methods. Method number 1 was northwest corner rule, NWCR. We have already obtained the solution using NWCR. Now least cost method, it went on finding out the lowest cost in the matrix and we made allocation. In the process we saw that there was an improvement in the cost reduction took place. From 1830 we went down to 1610. Only difference was in respect of 1830, that is northwest corner rule, we got only 6 allocations, whereas using the least cost method we got 7 allocations. The number 7 is important for reasons which I will explain later. Now I am finding out the phase 1 solution or IFS or BFS. Phase 1 solution, I can call it phase 1 solution, or I can call it basic feasible solution BFS, or initial feasible solution IFS. Any one of the 3 names I can call by using the third and the most important method, that is Vogel's approximation method. Now you will immediately ask a question. If a question like this comes in the exam, which method are we supposed to follow? If nothing is mentioned in the question, you are required to follow the last method. Sometimes the question may be specific. It may say obtain the initial feasible solution or basic feasible solution using LCM or least cost method, in which case I must use LCM because it is specifically mentioned. But if nothing is given in the question as to how to obtain the phase 1 solution, I must obtain the solution using Vogel's approximation method. Okay. So that is the method. Most important and tougher than the previous 2 methods is Vogel's approximation method. Remember, the effort involved in Vogel's approximation method is higher, but usually you will get the best solution. Now in some specific cases of problems, you may not get a solution as good as LCM sometimes. Sometimes LCM may be a better solution, sometimes Vogel's approximation method be a better solution. But let's see now, after completing the solution, we'll see which of the 3 methods gave us the least cost. But when nothing is mentioned, we must obtain IFS using Vogel's approximation method or VAM. So we are starting with VAM. Look at the matrix here. I have copied the matrix once again. This matrix is what? Same cost and same destination, demand and supply I have taken. Now this matrix, as you will see, 5 by 3 matrix, same matrix as before. Here we obtained IFS by NWCR, here by LCM, here I am obtaining by VAM. This method aims at minimizing penalty. Let me define what is penalty. Okay. Now look at this row number 3, for example. What are the various numbers in row number 3? The various costs are 7, 3, 11. If nothing else is given to you and you are required to make an allocation in row number 3, where will you make it? Obviously in the least cost cell, which is 3. I am looking at O3. Okay, I am looking at O3 for the time being. In O3 row, what are the costs? 7, 3 and 11. Which one would you choose? I will obviously choose the least cost, which is 3. But if for some reason you are not able to make allocation in row 3 over here, which is the next best cost? The next best cost would be 7. In other words, as you can see, 3 becomes 7. Lowest cost is 3. The next lowest cost in row number 2 is 7. But the difference between the two, 7 and 3, is 4. This is the penalty. What is a penalty therefore? A penalty is the additional cost for a row or column in which is under consideration. If you are unable to make allocation in the least cost cell, the additional cost of making allocation in the next least cost cell. Okay, that is the penalty. In other words, penalty for each row and column, how is it calculated? For example, look at row number 1. Row number 1, what is the least cost? 5. What is the next least cost? 7. What is the difference between the two? 7 minus 5, 2. That means penalty for row number 1 is said to be 2. Look at row number 2. Lowest cost is 4. Next lowest is 9. Difference between the two is 5. Therefore, penalty for row number 2 is 5. Penalty for row number 3, I have already said, it is 4. Penalty for row number 4. 9 and 5. That means 4 again. What is the penalty for row number 5? All the costs are 0. So lowest is 0, next lowest is also 0. So 0 minus 0, the penalty for row number 5 is 0. So this way we calculate penalty for each row, and similarly we calculate penalty for each column as well. Now look at column number 1. Remember, 0 is to be considered as a real cost. Okay. Now in column number 1, the lowest cost is 0. What is the next lowest in column number 1? It is 7, either this 7 or this 7. What is the difference between 7 and 0? 7. That means the penalty for associated with column number 1 is 7. And what is 7? Difference between two least cost in column number 1 is 7. Difference between two least cost in column number 2. Lowest cost is 0. Next lowest is 3. Therefore, 3 minus 0, the penalty for column number 2 is 3. Penalty for column number 3. Lowest cost is 0. Next lowest is 4. So 4 minus 0, difference between two lowest cost is 4. Therefore, penalty associated with column number 3 is 4. We calculate the penalties for each row and column. Now the space which is there on the left hand side of the matrix and at the top of the matrix, I am going to use this for writing the penalties. Now look at row number 1. As I said, difference between two lowest costs in row number 1 is 7 minus 5, that is 2. 9 minus 4, two lowest costs in row number 2 are 9 and 4, so the penalty is 5. 7 and 3, so the penalty is 4. 9 and 5, so the penalty is 4. 0 and 0, so the penalty is 0. Okay. These are called as row penalties. What are row penalties? Examine each row, find out the lowest cost and the next lowest cost. Difference between these two is the penalty associated with that row. Similarly, we will calculate penalties associated with the columns. Okay. Column number 1. Lowest cost 0, next lowest is this 7 or this 7, whichever, it does not matter. But the difference between two lowest cost is 7 minus 0 or 7. Second column. Lowest cost here 0, next lowest 3, penalty is 3. Last column. Lowest cost 0, next lowest is 4, so therefore the penalty is 4. So what are the various penalties? The row penalties are 2, 5, 4, 4, 0. The column penalties are 7, 3, 4. And therefore, now let me write down the penalties for each row and column. This is the penalties are 2, 5, 4, 4, 0. And the column penalties are 7, 3, 4. These are all the possible row and column penalties. What are the row penalties? 2, 5, 4, 4, 0 written on the left hand side. The column penalties are 7, 3, 4 written on the top side of the matrix. So out of these penalties, see, what is the objective of this method? The objective of this method, or the method which is followed in this algorithm using WHAM, is to minimize penalty. And penalty is the difference between two lowest cost, either in the row or in the column. If it is difference in the two lowest costs in the row, it is a row penalty. If it is difference between two lowest costs in the column, it is a column penalty. So what are the various penalties? If I write them all together, they are 2, 5, 4, 4, 0, 7, 3, 4. Out of them, choose the highest. Highest is 7. Out of all the penalties put together in one basket, choose the highest penalty, which is 7. And what is 7? 7 is penalty for column number 1. In other words, the penalty which I am choosing now is column number 1 penalty. Remember, the objective of the method is not minimizing cost, it is minimizing penalty. Okay. Therefore, the highest penalty threatens me most. I do not want a situation that the highest penalty will have to be incurred. Therefore, initially, at every stage, I am looking at the penalties, I am choosing the highest possible penalty. The highest possible penalty happens to be in respect of column number 1, that penalty is 7. Therefore, 7 is the penalty which I am trying to minimize. Okay. Now remember, 7. 7 was difference between which two numbers? In column number 1, if you see, the lowest cost was 0 and the next lowest cost was 7. Okay. So if I want to minimize the occurrence of the penalty 7, what do I need to do? I want to do something whereby I don't have to incur the penalty of 7. How do I do that? Between 7 and 0, if I make maximum possible allocation here, I will not have to go to 7. Correct? So this is what I am going to do. First, choose the highest penalty out of all the row and column penalty. The highest penalty is 7. This is a column penalty. Therefore, look at the column. What is the lowest cost in the column? 0. This is the cell which I am targeting for making my first allocation. What is the allocation that I am making? Obviously, the highest possible allocation. Look at the availability. Availability is 50. Demand is 120. That means I can allocate maximum 50 units in this particular cell. So I'll make allocation of 50 units. Remember, this is my first allocation using Vogel's approximation method. Recollect, how did I choose this cell for making allocation? I first worked out all the possible penalties for rows and columns. The row penalties were 2, 5, 4, 4, 0, and the column penalties were 7, 3, 4. Out of all row and column penalties put together, the highest possible penalty was 7. Therefore, I chose 7. Now, what happens if the two penalties are equal? We'll come to that. If that situation comes, we'll come to that. So 7 was the highest penalty. I put a tick mark on 7. Where is 7 happening? In column number 1. So choose this penalty. Now, my objective is not to incur this penalty. I do not want to incur this penalty. When will I incur this penalty? If I am not able to make allocation in the least cost cell in this column, then there is a question of going to the higher cost, which is 7. Therefore, I will create a situation that as far as possible, I don't have to go to this penalty. Therefore, I will make maximum possible allocation in the least cost cell in the column where the penalty is highest. The least cost cell in column number 1 is 0. And in respect of this cell, what is the address of this cell? It is O5D1. O5D1 cell is such that the availability is 50 and the demand here is 120. Therefore, the maximum allocation which I can put in cell O5D1 is limited to lower of the demand and supply, that is 50. So I made allocation of 50. After making allocation of 50, you will see one thing, that this particular availability at row number O5 is fully finished. Therefore, I need to delete this row. What happens to the demand of this column? The demand of this column was 120, of which I have already supplied 50 units. Therefore, the balance demand is 120 minus 50, that is 70. Good. So, first allocation successfully made. Now, look at this situation. I have deleted one row. Row number 5 stands deleted. Can you see therefore that from each column I have deleted one cell? From this column I have deleted this cell, from this column I have deleted this cell, from this column I have deleted this cell. That means cancellation of a row results in cancellation of one cell from each column. Therefore, there is every possibility that the column penalties may have undergone a change. because the least cost is gone from each column. Remember, 0 was the least cost in each column. Therefore, the moment I delete a row, the column penalties may have undergone a change, and therefore, once I delete a row, I need to recalculate the column penalties, which I will do. As you will see, the penalties are changing. What are the existing penalties? 7, 3, 4. Cancel them. Rewrite the new penalties. Okay. Now, what is column number 1? The column number 1, what are the various costs? 7, 12, 7, 9. This 0 is gone, so I am not considering this. So, what are the least cost in column number 1? 7. Which is the next least cost? Also 7. So, what is the penalty? 7 minus 7. That means the penalty has become 0. Okay. Column number 1, penalty has changed. It was 7 earlier, now it is 0. What about column number 2? What are the various costs in column number 2? 10, 9, 3, 5. Lowest is 3, next lowest is 5. Therefore, difference between the two, which is 5 minus 3 or 2, is the new penalty for column number 2. Okay. What about column number 3? The least cost in column number 3 is 4. The next least cost is 5. That means the penalty has become 5 minus 4 or 1. Now, what are the new penalties? Remember, the column penalties which were earlier 7, 3, 4 have drastically changed and they have become 0, 2, 1. And what are the row penalties? Row penalties are intact because row number 1, 2, 3, 4 we have not touched. Therefore, the row penalties are still intact. So, what are the total penalties now? Row penalties 2, 5, 4, 4, column penalties 0, 2, 1. Therefore, choose out of this the highest possible penalty. Can you see that out of 2, 5, 4, 4, 0, 2, 1, the highest is 5. And that happens to be a row penalty. Therefore, I am choosing this row penalty. Okay. In other words, my next allocation is going to be in row number 2, which has highest penalty associated with it, which is 5. Now, this 5 is difference between which two numbers? This 5 is the difference between 9 and 4. So, the lowest cost is 4 and the next lowest is 9. If I don't want to incur this penalty of 5, I need to make allocation in the least cost as much as possible. So, what is the allocation which I can make in this cell? Address of the cell is O2 D3. Availability at O2 is 50. Demand at D3 is 110. Therefore, the maximum allocation which I can make in cell O2 D3 is lower between 50 and 110, that is 50. So, I am making allocation of 50. I made allocation of 50. After every allocation, either a row or a column will get deleted. So, what is getting deleted here? If you see, this is 50, this is 50, that means row availability has been finished. Therefore, I am deleting this particular row. And what happens to 110? It is 110 minus 50 or it becomes 60. Fine. So, once again, I have deleted a row. When I delete a row, remember the column penalties will undergo change. When I delete a row, the column penalties undergo change. When I delete a column, row penalties will undergo change. In other words, I need to rework the penalties for columns once again since I have deleted a row. So, I am rewriting the penalties. Since there is no place, I am removing the old penalties. They are of anyway no consequence right now. So, I am rewriting the penalties for the columns. Now, look at column number 1. What are the costs in column number 1? 7, 7, 9. Two lowest costs are 7 and 7. So, the penalty is 0. Column number 2. 10, 3 and 5. Two least costs are 5 and 3. So, the penalty is 2. What about this column? Lowest cost is 5, 5, 11, 7. Lowest is 5, next lowest is 7. That means the penalty has become 7 minus 5, which is 2. Do you see that there was a change in the penalty? Previous penalty was 1, difference between 5 and 4. Now it is difference between 7 and 5, which is 2. So the penalty for the column has actually undergone a change. What are the new column penalty therefore? 0, 2, 2. Okay, good. What are the row penalties? No change in the row penalties. They remain 2, 4 and 4. This penalty has been taken care of. So this row has gone. So there is no question of calculating the penalty for row number 2. What are the row penalties? 2, 4, 4 and column penalties are 0, 2, 2. Fine. What is the highest penalty now? Remember 2, 4, 4, 0, 2, 2. The highest penalty is 4. Okay. 4, but 4 is happening at two places. Row number 3, the penalty is 4. Row number 4 also the penalty is 4. Which one do we choose? There are various ways of doing it, but one of the correct ways of doing it is, okay, examine this penalty, examine this penalty. I am examining this penalty. This penalty is difference between what? This penalty is difference between 7 and 3, which is 4. This penalty is difference between 9 and 5, which is also 4. So if I choose this penalty, I will be making allocation over here. If I choose this penalty, I will be making allocation over here. So for this penalty, the least cost is 3. For this penalty, the least cost is 5. Since my overall objective is cost, I will consider that penalty of 4 which results in lowest possible cost. This penalty of 4 results in a cost of 3. This penalty of 4 results in a cost of 5. Therefore, I will choose this penalty of 4 and not this penalty of 4. So, choose this penalty of 4. Okay. Row number 3 has been chosen to make allocation. What is the least cost in this row? As already said, it is 3. Okay. And in this 3, what is the address of the cell? O3D2 is the cell. O3D2. Cost is 3. Availability is 80. Demand is 100. Therefore, the maximum allocation which I can make in cell O3D2 is therefore 80, and I will make allocation of 80. I made allocation of 80. After every allocation, either a row or a column needs to be deleted. What is getting deleted here? Since supply is exhausted, the row stands deleted, and therefore I delete this row. What happens to the demand? The demand was 100, out of which I have already satisfied the demand to the extent of 80. So what is the balance demand therefore? 100 minus 80 or 20. Fine. Can you see that once again I have deleted a row? That means column penalties need to be calculated once again. Let me calculate the penalties. Now see, row penalties, there is no difference here because this row is intact. This row is intact, therefore there is no difference in this penalty. But since I have deleted this row, can you see that the column penalties are actually undergoing a change? What are the costs in this column now? Out of 5 rows, 3 rows are deleted. Therefore, what is the penalty? Difference between 7 and 9, which is 2. In case of this column, difference between 10 and 5 is 5. Suddenly a new high penalty has emerged as 5. Difference between 5 and 7, same old penalty continues, but I cancel the old penalty, rewrite the new penalty. Okay. Now, what are the penalties? Row number 1, penalty was always 2 because we have not done any changes to row number 1. Row number 4, the penalty was always 4. So, the row penalties are 2 and 4. What are the column penalties? 2, 5 and 2. So, out of rows and column penalties put together, 2, 4, 2, 5, 2, the highest is 5, and that is a column penalty. Therefore, I will choose the column penalty of 5 out of all these penalties, and therefore 2, 4, 2, 5, 2. These are the penalties. Highest out of them is 5. Therefore, I am putting a tick mark on 5. That means column number 2 is what I am looking at to make my next allocation. How do I make an allocation? First, I choose the penalty. Now, that happens to be a column penalty. In that column, I choose the lowest cost. And what are the costs? 10 and 5. So, this is the lowest cost. That means I need to make allocation in this particular cell. Availability is 60, demand is 20. That means I cannot make more than 20 units of allocation here. So, I will make allocation of 20 units. Now, with this, can you see that for the first time we are deleting a column? Because this 20 will take care of this demand of 20, but out of 60, only 20 are transported. So, this 60 will become 60 minus 20 or 40. New availability becomes 40, but column number 2 will have to be deleted because column number 2's demand was 100 totally, 80 and 20 makes it 100, and therefore, columns 2 stands deleted. Okay. Now, remember, we have deleted a column. When I delete a column, row penalties are to be changed. What are the row penalties now? Let me look at the row penalties. Column penalty, there is no change. This 2 and this 2 will remain same. But what about the row penalties? 7 and 5. So, the penalty is 7 minus 5, that is 2. So, I will cancel the old penalty 2, rewrite the new penalty also as 2. What about this row? 9 and 7, 2, once again. Now see, previously it was difference between 9 and 5, which was 4. Now it is difference between 9 and 7, which is 2. So the penalty of a row has actually changed. So what are the row penalties now? 2, 2 row penalties. Column penalties also 2, 2. Which one do we choose? Issue. Whichever I choose, the penalty is 2. So since our overall objective is to minimize cost, we will choose that penalty of 2. There are 4 penalties of 2. 2 row penalties are 2, 2 column penalties are 2. So I will choose that particular row or column penalty where the cost is lowest. This penalty of 2 results in lowest cost of 5. This penalty of 2 results in lowest cost of 7. Okay, so this penalty is better than this penalty of 2. Okay, what about columns? This penalty of 2 results in lowest cost of 7 and this penalty of 2 results in lowest cost of 5. That means this penalty of 2 and this penalty of 2 chooses the same cell for making allocation. Whether I choose this penalty of 2, in which case the allocation will be here, or whether I choose this penalty of 2, the allocation will still be here. So I can put a tick mark either on this penalty or on this penalty because the resultant allocation is same. So I can put a tick mark here or for that matter here or for that matter both the places. Okay, now fine. So this is the cell therefore which is the result of choosing this penalty. What is the allocation which I can make here? Now see, availability is 90, demand is 60, lower of the 2 is 60. That means I can allocate maximum 60 units over here. And therefore the column will stand deleted. 60, 60, column will stand deleted. Out of 90, what is left is 30. Fine. Now, has our favorite situation come? When only one column is left. When only one column is left, you have no choice about making allocation. And see, what are the balance availabilities? 30 here and 40 here, making a total of 70. And the balance demand is also 70. Because this was a balance problem, at every stage, the residual problem will always be a balance problem. So I must make allocation of 30 here and 40 here, and that will take care of the entire allocation. So last two allocations, 30 here and finally 40 here, making a total of 70. So the column goes out and 2 rows go out. So this column goes out. All the rows and columns have been cancelled. Great. Now let's see. Is this allocation different than this allocation? Yes, it looks like the LCM allocation is different than this allocation. We need to find out which is better. Sometimes it could be this, sometimes it could be this. But let's find out the cost. Now this was allocation called as what? VAM, Vogel's approximation method, or VAM. This was NWCR, this was least cost method, and this is VAM. Now if you compare this least cost method solution with the VAM solution, they are different. Some of the allocations may be same, but other allocations are not necessarily same, and therefore let us find out the cost of this matrix. Fine. So 30 into 7, I'll take the total somewhere. Now here I'll write the total. 30 into 7, 210, 60 into 5, 300, second row 50 into 4, 200, third row 80 into 3, 240, next row 40 into 9, 360, 20 into 5, 100, and 50 into 0 is 0. So what is the total? Let me check. 1410. So the three methods have given three costs. Method number 1 gave a cost of 1830, method number 2 gave a cost of 1610, and VAM, which is normally the most efficient method, has given at a cost of 1410. And the number of allocations, count the number of allocations here, 1, 2, 3, 4, 5, 6, 7. 7 allocations. So we got 7 allocations in both LCM and VAM, but in respect of NWCR, we got only 6 allocations. But the cost, they do not compare. The cost of NWCR was 1830, 1830. The cost obtained by LCM was 1610, and the cost obtained by VAM was 1410. The most efficient of the solutions obtained is 1410. This is the best solution out of the 3 methods, because our objective is what? Minimize the cost. We have already got a better solution using VAM. Okay. So now this is the end of phase 1. Phase 2, what are we doing? We take the solution obtained in phase 1 and examine whether it is optimal or not. If it is optimal, our job is done. Then we are through. Okay. But before going to phase 2, we will be solving one more problem and obtaining only IFS. For this particular problem, we will obtain the phase 2 solution little later. We will come back to this problem and do it. But before doing that, we will take up yet another problem, and in that problem, we will obtain the solutions once again using northwest corner rule, least cost method and Vogel's approximation method, and compare the solutions. Okay, which are the best cost out of the 3 methods. Okay, thank you. So next problem, we will obtain phase 1 only, and phase 1 solutions will be again 3: northwest corner rule, least cost method and Vogel's approximation method. That will be your question number 2. Okay, thank you.